Your eyes have a single layer of cells that send a 2D image to your brain. Somehow, from a 2D image, our brains are able to recognize three-dimensional shapes. Subtle cues, shading, perspective, shadows, give your brain the information it needs. Our 3D renderer's job is gonna be to take in some three-dimensional scene and reproduce those same cues on a flat screen. At the most fundamental level, a 3D renderer achieves these cues by breaking complex shapes into tiny flat triangles, projecting those triangles into a flat 2D image captured from a camera, shading or coloring those triangles in ways that trick the eye, and then sending that image to the monitor. By the end of this video, you'll understand this entire process, and you'll understand how this rotating, shaded cube was rendered entirely from scratch. Suppose we have a 3D scene filled with 3D objects, where each object is made from points, or vertices, and is colored according to its material. The rendering pipeline is going to take this scene and transform it into a 2D image. It does this by breaking the task into 3 steps. The first step is the vertex shader. The vertex shader takes in all the object's geometries and meshes, which is just a collection of points. The vertex shader will tell us where each vertex, or point, in the 3D world falls onto the 2D image we're going to send to the display, also called the view plane. Note that this frame thing around the camera is a view frustum and defines everything that the camera can see. Next, we have the rasterization stage. The rasterizer takes in the 2D image with the vertices and figures out what pixels cover what triangles. Note that the specific ordering of the vertices allows us to define the edges of each triangle. Lastly, we have the fragment shader. Fragment shader determines the final color of each pixel using textures, lighting, colors, and so on. In 3D graphics, a single vertex, and by extension, the entire model, travels through a series of transformations before it appears on screen. These transformations are encoded by matrices. Vertex first starts out in model space, meaning its coordinates are defined relative to the object it belongs to. In this space, the object's own origin is the reference. In the diagram, the arrow represents the object's position in model space. The start of the arrow is the object's local origin, and the end of the arrows is where the object is located relative to that origin. First, we multiply each vertex v by the model matrix. This calculation takes the position of the vertex v and transforms it so that it is now relative to world origin, not the object origin. Then we multiply each vertex v by the camera's view matrix. This transformation places the vertex in view space, the coordinate system relative to the camera. Every vertex is now positioned and oriented relative to the camera. Next, we multiply the vector v with the projection matrix and enter clip space. Clip space is a coordinate system that prepares vertices for the next stage, perspective division. In clip space, the GPU can quickly discard, or clip, vertices outside the view frustum, anything that the camera cannot see. In our case, the projection matrix applies perspective projection, where objects further away appear smaller. If we wanted, we could also use orthographic projection, where objects maintain their relative sizes. Next, we convert from clip space into normalized device coordinates. Here, NDCE maps all visible vertices into a cube from -1 to 1 in x, y, and z. This step makes it easy to then map coordinates to actual pixels on the screen. It is also useful to compute the depth value of the pixel, which tells us how far away a vertex is from the camera and is used in rasterization for depth testing. So, the vertex shader accepts the vertex model position, applies the model matrix to place that vertex into world space, applies the view matrix to place that vertex into camera space, applies the projection matrix to create clip space coordinates, performs perspective divide to get NDC, and then finally applies the viewport transform to obtain the pixel positions of each vertex. The vertex shader also passes along attributes like normals, UVs, or colors, which the rasterizer uses later on for coloring and shading. So, through a series of matrix multiplications, the GPU takes in all the vertices of our scene, defined relative to a camera, and computes where on our 2D screens those points would end up. Now that we have the vertices on a 2D image, we need to fill them in. The rasterizer fills in the pixels inside the points given by the vertex shader. But how do we actually do that? Well, if we can determine whether any given pixel on the screen falls inside a triangle, then filling that triangle becomes simple. We just loop over every pixel, check if it's inside, and color it if it is. And since any complex 3D scene can be broken down into triangles, this method applies everywhere. Even objects that appear to be curved just have a lot of straight triangles. One common way to test whether a pixel is inside a triangle is to use barycentric coordinates. For pixel position P and triangle vertices A, B, C, we can express P in terms of those 3 points, where alpha, beta, and gamma are weights that we compute from the triangle itself. If alpha, beta, and gamma are all between 0 and 1, and they add up to 1, the point P is inside the triangle. If any of the weights is negative, P is outside. Running this function for every pixel allows us to render a triangle. From the vertex shader, when we computed the XY position of each pixel, we also got a depth value. This depth value is stored in a depth buffer, which stores the closest depth seen so far. The GPU uses it to prevent a farther triangle from overwriting a nearer one. The cube example, the reason the back face doesn't overwrite the front face is because the back face has a higher depth value than the front face, which the GPU uses to decide that it won't overwrite the first face. Note that because triangles can intersect, the depth value has to be computed for each pixel, which is computed using a technique we'll see in a second. Now, if we want our cube to have more complex coloring, we have to use textures. Texture is just an image, but to put that image on a model, we need a way to tell the renderer which part of the image belongs to which part of the mesh. That's what UV coordinates do. Each vertex in a model gets a pair of numbers, called U and B, that point to a location on the texture. U moves horizontally across the image from 0 to 1, and V moves vertically from 0 to 1. It's kind of like stretching a sticker over the model. UVs tell you exactly where each corner of the sticker touches the geometry. In the previous step, when the rasterizer fills in the triangle's pixels, it uses these UVs to figure out which part of the image each pixel should take its color from. This way, a flat 2D image can wrap smoothly over a 3D object. Now let's look at the fragment shader. Fragment shader decides the final color of the object using material data, lighting, shadows, and other effects. Lighting is fairly simple. When the light hits a surface, the brightness mostly depends on how directly the surface faces the light. If the surface is facing the light perfectly head-on, it looks bright. If the surface is tilted away, it looks dimmer. Computers figure this out using a little math between the surface normal, which is like a little flag sticking out of the surface showing which way it faces, and the light direction. The more these two arrows are aligned, the brighter the surface. The less they are aligned, the darker the face becomes. Now, if we compute lighting once per face, every pixel on that face gets the exact same lighting value. Each face is still a single, flat shade with harsh cutoffs. To fix this, we compute lighting per vertex instead of per face and then interpolate those lighting results across the triangle using those same barycentric coordinates we used to fill the triangle. This gives us realistic lighting, where each color of the face transitions properly. Note that interpolation with barycentric coordinates is exactly how we computed the Z depth for each pixel in the rasterization phase. Up to now, we've only talked about diffuse lighting, which shades each surface uniformly. To achieve more realistic results, we also need to include focus lighting effects known as specular reflection. Specular lighting shades part of the object differently depending on if the camera is looking from the right angle to see a bright reflection. This depends on the light direction, the view direction, and how smooth or shiny the surface is. If everything lines up just right, a small bright spot appears, called the specular highlight. To get realistic lighting, we must combine both diffuse and specular lighting. Using everything we have so far, we can create a simple cube, and using the model matrix, we can rotate the cube nicely. Lighting alone makes objects appear three-dimensional, but without shadows, the scene still looks wrong. Lighting only tells us how much light should hit a surface if nothing blocks it. In the real world, objects block light from reaching other objects, so we need to know, for each pixel we draw, whether something is sitting between that pixel and the light. To figure that out, we use something called shadow mapping. The idea is simple. First, pretend the light is a camera. We render the scene from the light's point of view and restore the distance from the light to the nearest surface at each pixel. This produces an image called the shadow map. The shadow map answers the question, from the light's perspective, what is the closest thing in its direction? Later, when we render the scene normally from the real camera, each pixel also knows its world position. We transform that position into the light's coordinate space using the light's own projection matrix, the same way the vertex shader transformed vertices for normal rendering. This tells us where this pixel would appear in the shadow map. Now we compare two distances, the distance from the light to our pixel and the distance stored in the shadow map at that same location. If the pixel's distance is greater than the depth stored in the shadow map, that means something else is closer to the light than the pixel is. In other words, the pixel is hidden from the light, so it should be in shadow. If the distance is matched, the light can see the pixel and it gets normal diffuse in specular lighting. But the core idea stays extremely simple. To know if a point is lit, check whether it is the nearest surface to the light in that direction. If it isn't the nearest surface to the light, then something else is closer to the light, which means that the point is in a shadow. Summarize: matrix multiplied by a vertex is how we tell the GPU to move, rotate, and scale that vertex. The vertex shader applies those matrices, producing positions that the rasterizers can turn into pixels. Fragment shader then calculates shadows on specular and diffuse lighting, all of which can simply be computed using the direction of the light, the direction of the surface, and the direction of the camera.